Good morning to one and all. See this. In this today's live lecture, we shall study integrand as product of functions. Means here in this case, we shall discuss the integration of a product of functions which is in the form of improper integral and improper integral as infinity, convergent at infinity. That means integrand as a product of a function for convergence at infinity. This concept we have to study. Prithviraj Jadhav, Mukund, Vaishnavi, शिंदे, इमदे, बिरादार, पवार, साळुंके, वाघमारे, योगेश एवढे चालेत का विद्यार्थी? So now see this, we have to discuss this integrand as a product of a function. Actually this is the fourth unit and this is the last part of this fourth unit, that is integrand as a product of functions, and in a bracket that is a convergence at infinity. So there is one theorem. Actually we have defined in the last lecture, we have defined absolute convergence at infinity. The improper integral from a to b f dx is said to be absolutely convergent if integral from a to infinity mod f dx is convergent. That is, integral from a to infinity mod f dx is convergent, then we can say that integral from a to infinity is convergent absolutely. Okay, is said to be convergent absolutely. Now we shall discuss the last part, that is integrand as a product of function, means integration of product of two functions. Integration of product of two function which is in the improper integral form and convergence at infinity we have to discuss. First of all, we have to study one theorem, proof of this one theorem, and then we shall go towards the problem based on this. Integrand of product of two functions, product of functions, okay. See this. Now we shall discuss one theorem based on, suppose f and g are two functions. Suppose f and g are, let f of x and g of x be the two functions of x in the given domain, then the improper integral from a to infinity f of x into g of x dx, or integral from a to infinity f into g dx is said to be integrand of a product of a function. Now here in this case, here in this section, we shall study the convergence of integrand of integrand is a product of a function product of functions at infinity. See this, integrand is a product of two functions means f of x and g of x be the two functions of x in the given domain, then the improper integral from a to infinity f of x into g of x dx or f into g dx is said to be integrand is a product of two functions. Now in this section we shall study the convergence of the integrand is a product of two functions. Now how we can say that the given integrand as a product of two function is convergent, how we can say that the given improper integral is divergent. So in this section we shall discuss that matter. Okay, now test for absolute convergence, theorem number कितवा है रे स्टूडेंट बघा बरं. A test for absolute convergence, a test for absolute convergence. Now theorem कितवा है रे निर्मोही, योगेश, गोरे, धनश्री, दर्शन गोरे, ऋतुजा मद्रेवार, theorem number. Okay, the statement of the theorem is a function, okay, 9, theorem number 9, a function phi is a bounded, okay, 9, bounded in semi-closed interval a comma infinity, infinity side open असते हां, and integrable in closed interval a comma x, where capital X is a number greater than or equals to a. Okay, full stop. If integral from a to infinity f dx, see this, integral from a to infinity f dx is absolutely convergent at infinity, then prove that integral from a to infinity f into phi dx is also absolutely convergent at infinity. This is the statement of the theorem. Integrand is a product of a function. दोन फंक्शनचा प्रोडक्ट आहे f आणि phi. F and phi are the two functions. So this is the integral which is the product of two functions f and phi, and this integral is improper integral because its right end is at the infinity. That means the range of this given integral is infinity. So this is improper integral. Now we shall discuss the convergence of this improper integral, which is in the form of a product of two functions, in this section. So I shall read this statement of the theorem again. A function phi is bounded in semi-closed interval a comma infinity and integrable in closed interval a comma x, where capital X is a number which is greater than a, if integral from a to infinity f dx is absolutely convergent at infinity, then prove that integral from a to infinity f into phi dx is also absolutely convergent at infinity, is also absolutely convergent at infinity. See this. Now we shall start the proof. आता आपण proof घेऊ. Proof. What we have given here, actually we have given that the function phi is bounded in semi-closed interval a comma infinity, and it is integrable in closed interval a comma x. So we can write this as, 1 minute, given that the function phi is bounded in semi-closed interval a comma infinity, then according to the definition of a boundedness, according to the, then there exists, we can say, then there exists a constant, a positive number, there exists a positive number k such that if f of x is said to be bounded, then there exists a positive number capital M such that mod of f of x is less than k. You know that. But here in this case already given function is from a to infinity. Okay, a is a positive. So we can write, this implies that therefore mod of phi of x which is less than or equals to k for all x is greater than or equals to a. But a is a positive, then we can definitely say that, so phi of x which is less than or equals to capital K for all x greater than or equals to a. Also we have given phi is integrable. आणखी काय दिले पहा, तुम्हाला आठवत आहे का? Also we have given the function phi is integrable. तुम्हाला माहित आहे phi हा इंटिग्रेबल आहे. इंटिग्रेबल असल्यामुळं it will be having the integration, पहा डेफिनेशन मध्ये काय सांगितले थेरमच्या स्टेटमेंट मध्ये, and integrable which is given by integrable. So we can say that the function phi is also integrable. Also given that the function phi of x is integrable in closed interval a comma capital X. Then according to the definition of the integrable function, we can write the value of this function is less than or equals to any number, real number. Then by the theorem, we can write integral from a to capital X phi of x dx which is less than or equals to, suppose any number, we can consider that number as we can consider that number as suppose n, where n is the positive number, and a x is greater than a. Theorem पाहिला पहा, where n is the positive number. Suppose this is equation second, Actually this is given already, we have given integrable in the closed interval a for x is greater than or equals to a. Now also we have given integral from a to infinity f dx is absolutely convergent. हे पण दिलेलं आहे, absolutely convergent. So also integral from a to infinity f dx is absolutely convergent. This implies that, याचाच meaning काय असतो, integral from a to infinity mod f dx is convergent according to the definition of the absolute convergence. See this, yesterday we have seen the definition of the absolute convergence. Absolute convergence, the improper integral from a to infinity f dx is said to be absolutely convergent if integral from a to infinity mod f dx is convergent. This is the definition of the absolute convergent. बरोबर आहे का रे स्टुडंट्स? absolute convergent. थांबा मी स्क्रीनशॉट घेतो, मुलं काय आन्सरच देत नाहीत, विचारलं तर बोलत नाहीत, विनाकारण व्हिडिओ लावून कुठं तरी जातात. सो the concept regarding the absolute convergent, according to the definition of the absolute convergent, we can write, काय definition लिहावं लागेल रे? According to the definition of अमृता गोरे, एवढ्या लेट जॉईन नाही व्हायचं. According to the definition of the absolute convergent, we have given, actually we have given integral from a to infinity f dx is convergent. This implies that integral from a to infinity mod f dx is convergent. Mod f dx convergent. See this, this is the first part of this theorem. What is the first part? Phi is bounded, then according to the boundedness we can write. Then secondly, phi is integrable in the closed interval a comma x, then according to the theorem of the integrability, theorem number first, integral from a to x phi of x dx which is less than n for all x is greater than n. So this is the definition. आता third definition काय येते पहा? Third definition काय येते? We have to write the third definition. We have given integral from a to infinity f dx is absolutely convergent. Then according to the theorem or definition of the absolute convergent, we can write a to infinity mod of f of x dx. These are the total terms which are as per given. आता पहा, mod of f dx convergent असेल तर आणखी असाच theorem होतो. convergent म्हटलं की इंटिग्रेबल म्हटलं की convergent येतो, मग अशा पद्धतीने येतं. So by the definition, therefore there exists a number capital M such that, आता हा इंटिग्रेबल आहे ना, so we can write integral from a to capital X mod of f dx which is less than or equals to capital M, and for all x greater than or equals to a. इथं पण लिहा for all x greater than, same definition. Suppose this is equation number 3. Now using the equation 1, आता equation 1 वरनं, using the equation 1 we can write, we have, now we have from 1, suppose mod of f into phi which is equals to mod f into mod phi which is less than or equals to, mod phi is less than or equals to k, so mod f into k, therefore mod of f into phi which is less than or equals to k into mod f. Suppose this is equation number 4. पहा ना, mod f into mod phi ची व्हॅल्यू कॅल्क्युलेट केली, because we have to show that integral from a to infinity f into phi is absolutely convergent दाखवायचं आहे. म्हणून mod f into mod phi ची व्हॅल्यू कॅल्क्युलेट केली. That will be k into mod f for all x belongs to x is greater than or equals to capital X. इथं लिहा वाटलं तर for all small x is greater than or equals to capital A. So this is equation number 4. इथं स्मॉल f of x आणि phi of x असल्यामुळे ती घेतलं. नाव इंटिग्रल फ्रॉम a to x, आता हे इंटिग्रल आपल्याला काय दाखवायचं आहे, कॉन्व्हर्जंट दाखवायचे आहे. मॉड ऑफ f into phi dx which is equals to integral from a to x mod f into mod phi. Already we have seen mod f into mod phi means k into mod f. From 4 we can write k into mod f. This is dx from 4. So we can write which is equals to k into integral from a to x mod of f of x dx. So therefore integral from a to x mod f into phi dx which is less than or equals to, आता integral from a to x mod f dx is less than or equals to m from 3. So we can write which is less than or equals to, put k as it is and less than or equals to m. Equals to चं रूपांतर less than मध्ये, कारण इथं less than or equals to होतं पहा. Integral from a to x mod f of x dx is less than or equals to m. जेव्हा तुम्ही आता m रिप्लेस करणार इथं, तेव्हा इक्वल्स टू च्या जागी काय रिप्लेस करावं लागेल तुम्हाला, लेस दॅन ऑर इक्वल्स टू, बिकॉज वी आर रिप्लेसिंग दिस mod f is less than or equals to m. So we have to replace this. This can be written as from 3. So we get therefore integral from a to x mod f into phi dx which is less than or equals to k into m. Now k is any real number, k is a positive real number, m is the positive real number. So km is also any positive real number for all x greater than or equals to a. And this implies that this integral is bounded. This implies that the positive function, integral from a to capital X mod of f into phi dx is bounded. Less than or equals to k into m. K is real number, m is any positive real number. Less than or equals to positive real number means bounded, is bounded above by km for all x greater than or equals to a. And this proves that integral from a to x mod f into phi dx is convergent or converges. इज लिहायची गरज नाही, कॉन्व्हर्जंट लिहिलं तर इज लिहा. अँड हेन्स प्रूव्ड, हा सिंपल थेरम आहे स्टुडंट्स. दिस इज ॲक्च्युअली व्हेरी सिंपल थेरम, काहीच अवघड नाही. दिलेल्या कंडिशन व्यवस्थित प्रॉपरली पुटअप करा. दिलेल्या कंडिशन व्यवस्थित प्रॉपरली पुट केल्यानंतर जो रिझल्ट येतो तो म्हणजे हा आहे. काही अडचण नाही. कुठं जरी अडचण आली, इफ यू हॅव एनी डाऊट देन यू कॅन आस्क मी. ओके, now we shall take example based on this. नाउ राइट डाउन प्रॉब्लेम. आता याच्यावरचे आपण प्रॉब्लेम्स घेऊ. ओके, इथे एक नोट टाकतो. नोट लिहा. नोट माहित राहावे. इफ integral from 1 to infinity f df of x dx which is equals to where एक मिनिट, 1 minute. Note, let f of x equals to, it has a two part, that is 1 by x square, where x is a rational number, and 1 upon x square minus 1 upon x square when x is irrational number. Then integral from 1 to infinity mod of f of x dx, mod of f of x dx which is equals to integral from 1 to infinity 1 upon x square dx. mod जरी कुठला असाल, रॅशनल असो इरॅशनल असो, पण जेव्हा ॲब्सोल्यूट व्हॅल्यू घेतात तेव्हा मॉडची व्हॅल्यू पॉझिटिव्ह होते. -1 अपॉन एक्स स्क्वेअरची व्हॅल्यू 1 अपॉन एक्स स्क्वेअरच होते, +1 अपॉन एक्स स्क्वेअरची व्हॅल्यू 1 अपॉन एक्स स्क्वेअरच होते. मीन्स एफ ऑफ एक्स इज इक्वल्स टू 1 अपॉन एक्स स्क्वेअर फॉर रॅशनल, -1 upon x square is for irrational. Then for the modulus function, integral from a to infinity mod f of x dx which can be written as integral from 1 to infinity 1 upon x square dx. आता हे कॉन्वर्जंट आहे का डायव्हर्जंट आहे सांगा रे प्रत्येकाने. हे जे इंटिग्रल आहे, नाउ यू टेल मी दिस इंटिग्रल फ्रॉम 1 to infinity 1 upon x square dx is convergent or divergent? You tell me. Now actually there is one theorem we have seen, useful integral. In that useful integral we have seen that if the integral is c upon x raised to n and n is greater than 1, then we can say that it is a convergent. Is convergent, which is equals to convergent. Therefore the given function is, therefore the integral from a to infinity, 1 to infinity f of x dx is convergent absolutely. Convergent absolutely. Okay, so this is a note. एक example, एक particular example घेतलेला आहे. Now we shall discuss one problem. Now we have to see one example based on this. Prove that integral from 1 to infinity sin x divided by x raised to p is convergent for p greater than 0. Answer, let I is equals to integral from 1 to infinity sin x divided by x raised to p dx. So now we have to distribute this function into two parts. First part we have to consider f, second part we have to consider phi, f and phi. So we can write this integral in the form of a product of two integrands. So let f of x is equals to sin x and phi of x is equals to 1 upon x raised to p. We have considered here two functions. Then f into phi, which is given by sin x divided by x raised to p. Now integral from 1 to x sin x dx which is equals to, आता इंटिग्रल फ्रॉम 1 to x sin x dx आहे, हे कॅल्क्युलेट करत असताना आपण मॉड्युलस फंक्शन मध्ये घेऊ. मॉड ऑफ इंटिग्रल फ्रॉम 1 to x अगोदर इथं घेऊ f of x dx, 1 minute, f of x dx which is equals to mod of sin x dx which can be written as sin x integration काय असतं रे स्टुडंट सांगा बरं. sin x इंटिग्रेशन that is minus cos x from 1 to x. So put this limit minus mod मध्ये minus in a bracket upper limit ठेवा cos x, lower limit ठेवा cos 1, that is equals to mod of cos 1 minus cos x, but which is less than or equals to integral from 1 to x f of x dx which is less than or equals to mod of cos 1 plus mod of cos x. Mod of cos 1, mod of cos x. आता we have cos x is less than or equals to 1 and greater than or equals to minus 1. So 0 is less than or equals to cos of mod x which is less than or equals to 1. 0 is less than or equals to cos 1 which is less than or equals to 1. That means cos x is mod cos x is less than or equals to 1. Mod 1 is mod cos 1 is less than or equals to 1. So this is less than or equals to 1, less than or equals to 1 means which is less than or equals to 2. Therefore we get integral from 1 mod f of x dx which is less than or equals to 2 for all 1 is less than or equals to x is less than or equals to infinity, less than infinity. Okay, this is the value of modulus of f of x, integral from 1 to infinity f of x dx. Also, आता दुसरा फंक्शन घ्या. What is the second function? 1 upon x raised to p. Also, suppose this is equation number 1. Also, phi of x is equals to 1 upon x square. Phi of x is equals to 1 upon x square है का काय रे? 1 upon x raised to p. Now 1 upon x raised to p means denominator is going on increasing. Denominator, if function of the denominator is going on increasing, numerator is a constant, that means this function is a monotonic decreasing function. This function is monotonic decreasing function to 0 means as x tends to infinity then 1 upon x tends to 0 होतो. म्हणजे x ची व्हॅल्यू इन्फिनिटी पर्यंत जावा त्या टोटल फंक्शन ची व्हॅल्यू 0 होते. म्हणजे इट इज अ बाउंडेड as x tends to infinity for p is greater than 0. म्हणून the function is a monotonic increasing and so it is a bounded. So phi of x is, therefore phi of x which is equals to 1 upon x raised to p is bounded. P is bounded. Okay, this implies that therefore we can say that integral from 1 to infinity f into phi dx, which is equals to integral from 1 to infinity sin x divided by x raised to p is convergent when p is greater than 0. Also we know that आपण प्रूव्ह केलं पहा, integral from 1 to infinity sin x divided by x raised to p dx is converges absolutely. आपल्याला हे माहिती आहे, आपण प्रूव्ह केलं आहे अगोदरच्या प्रॉब्लेम मध्ये, अगोदरच्या थेरमच्या कंडिशन मध्ये हे प्रूव्ह केलेलं आहे. फॉर p greater than 1 but not conditionally. Therefore, though this implies that integral from 1 to infinity sin x divided by x raised to p dx converges absolutely for p greater than 1 but not conditionally. But not conditionally for 0 is less than or equals to 0 is less than p, which is less than or equals to 1, and hence proved. Okay, अशा पद्धतीने हे काय होतं, प्रूव्ह होतं कॉन्व्हर्जंट. हा पुढचा पार्ट नाही केला तरी चालतो, इथपर्यंत केला तरी सफिशियंट आहे. इथपर्यंत हे एक तुम्हाला ॲडिशन माहिती असावी म्हणून वी हॅव गिवन. दिस इज द ॲडिशनल इन्फॉर्मेशन बट दिस इज द रिक्वायर्ड प्रूफ. हेच रिक्वायर्ड प्रूफ आहे ओनली. सो वी कॅन प्रूव्ह धिस रिझल्ट. अशा पद्धतीने हा रिझल्ट होतो. नाव आता आणखी एक थेरम राहिला, डिरिचलेट्स थेरम, अबेल्स थेरम. 1, 2, 3 थेरम आहेत, म्हणजे 2-3 लेक्चरमध्ये हा आपला टोटल सिलेबस संपून जातो. एक जास्तीत जास्त 3 लेक्चरमध्ये हा आपला सिलेबस संपतो. ओके, देन वी शॅल टेक द सेमिनार्स, आणि मग त्याच्यावरचे आपण काय घेऊ, सेमिनार्स घेऊ. ओके, नाउ वी शॅल स्टॉप हिअर. नमस्कार, गुड बाय. काय अडचण आहे का रे स्टुडंट्स? इफ यू हॅव एनी डाऊट देन यू कॅन आस्क. ओके, नाही काय अडचण नाही आहे ना?